Okay, cool. So last time we were talking about Monte Carlo, and in Monte Carlo, again, to recap, was we don't know the world we're in. We have these episodes that we can sample, create, or otherwise have access to, and now we can just sort of estimate the value function by way of looking at sort of the statistics of the data that we're able to collect. So temporal difference learning is actually Sutton and Bartow had this very strong statement to say about it, which is if it's one of the most important and the most novel ideas in reinforcement learning. So take that for what it's worth. I've seen this quote about TD learning included in almost every lecture and every paper or book I've read on the subject. So pretty common to bring this up. And again, to reiterate, a lot of the materials that I'll be talking about is from this lecture 3 from CS234 from Stanford. So I highly recommend watching that lecture if you would like to kind of go deeper on the subject, because it's a whole lecture on this stuff, and I'll just be spending a few minutes talking about some of these ideas. So temporal difference learning, the advantages is that it's model free, and it can be used both in the infinite and non-infinite horizon MDPs, meaning we don't need purely episodic learning. We could actually run this or run time, and your agent will just get better as you go. And so that's one of the really kind of good things here, right? With Monte Carlo, we had to sort of run it on a set of samples for us to get a new policy, whereas here we can actually run and benefit from the value function improving every single iteration. So we start to see this idea of that Bellman backup function, but with a model-free case. So again, let's kind of take this intuition and recall the Bellman backup operator, right, where the value of our value function, the operator, is going to be equal to, well, what's the reward we're going to get from the particular action we take in this state, right, plus the expected value of the next state that we're going to go into because of that action, right? And that can be across this sort of distribution of model, right? Again, we don't know this model distribution, but we can kind of pretend like we know there's some kind of likelihood of going into a particular set of states, and we can sort of treat this as this mathematical construct in our head. By taking an action, there's an expectation of that future state that we're going to be in for all the different states that we could potentially be in, right? So if for example, I take a left, and I'm either going to go left or right, I'm more likely to go left because I took a left, but there's a small chance I might go right. And I can say, well, going left is going to be worth 10 donuts, going right is going to be worth 1 donut, and there's 90% chance of going left, so that means the likelihood is I'm going to get 9.1 donuts, right? So whatever. And so in Monte Carlo, right, we're estimating the sort of value function by taking one sample from the return, as we saw this sort of TD target. TD target. I'm skipping steps. We saw this sort of target, right? This baseline. We have the baseline. We know what the return is. We're subtracting from it the value function of the particular state that we have estimated, and now we multiply it by some alpha, some rate of learning. This may look somewhat familiar to you from other things we've talked about in this course, and we add it to our estimate. So now we're sort of inching towards something. Now, wouldn't it be nice if we could do something similar to this without having to look at an entire episode to do so? So that's the insight here, right? We can essentially, instead of using this total, this return, we can stick in this expectation, this reward, plus the discounted value of the next state, minus the value of that of the current state that we have, right? This is sort of a mathematical construct or a mathematical expectation of the return. And so I think this is the intuition of how temporal difference learning is working. We have our value function, or value for the state that we have calculated. We're constantly iterating on this value function. Remember, right? We're adding to it some learning rate multiplied by what the difference between what we think, what we expect, and what we currently think. And so this is the idea. And because this is essentially a Bellman operator, this is actually proven to converge. And so that's the general idea, right? We are taking essentially our value function, and we multiply it. We add to it some kind of TD, like some kind of target. This target, in this case, being this right part of the equation, multiplied by a learning rate. And so in this case, what we're going to do is we're going to define the TD error, or the TD target, also as it's also known, as this difference between the reward that we get, the value we expect from the next state that we may be in, and minus the value of our current state that we got this reward from. And we can immediately update sort of our estimate on every single state action reward and then new state tuple that we get, because when we're in a state, we take an action, we get a reward and a new state, right? That's how we do it in every iteration in the agent. And so that's how we can do this. We can actually just do it. It works. Believe it or not. And you can do this with the action, the state action function, the same, literally in the same way. You just replace your state, the value function with the state action, with a Q function. And so it's a pretty simple idea, actually. There are different learning versions of this algorithm. We're going to talk about the TD0 algorithm, which has to do with just how many time steps do you operate on. I won't talk too much about that, but if that's interesting to you, please bring it up in the Discord. I'm happy to talk to it. But it's just about, or like you can see here in the TD target, we have RT plus this discount factor times the value from the next state, where you can kind of blow the value function for the next state up into RT plus 1, blah, blah, blah. So like you can do this with more than one step if you'd like. But yeah, this is it. This is the entire algorithm, right? We initialize our value function estimate to zeros for all states. We sample a tuple from the environment, and we plug it in, right? And like you can kind of imagine how it works in the first case, right? Right now our value function is 0, and we add to it basically everything in here is 0 except for the reward that we're going to get. So now, the first step you take, we're applying this alpha to the reward of that particular state that we're in. So you can kind of see how it'll just progress from there. It's a little bit outside of the context of this class, again, to talk about theoretically the convergence proofs and all this stuff. But if you're interested, please check out this lecture from and the set of lectures from the Stanford class that I pulled this slide from, because they go into much deeper technical rigor on this stuff. So this introduces us to our first sort of fancy algorithm, or at least one that has a name that isn't just sort of policy evaluation. So this is what's called SARSA, which is an on-policy TD control. So on-policy means that we're using our current policy, data from our current policy, not previous policies. I know it's kind of weird, but we'll see an algorithm right after this one that is an off-policy method. And what we're doing is we're going to be updating the Q value function by way of these tuples that we're sampling from the environment. And at every iteration, we're going to have a new estimate of our Q function. And so here on the right, let's go through the algorithm, right? And this is from actually Lillian Wang's blog that I just cut and paste because I'm lazy. So you start off at time 0, right? We start off with a state 0. Again, that's just given to you by your environment. And we choose an action that's going to be the maximum Q value from our given state. You might be like, well, what do we do in the first one? It's going to be all zeros. Well, we also use this thing called E-greedy, right, as we've talked about before. So with some percentage epsilon, we're going to just take a random thing. So you can kind of apply that to like the tiebreaker case as well. There's a variety of different ways to deal with ties, but let's pretend like we don't have to do it, or you can just randomly initialize Q. So at time t, after we apply an action t, we get rt plus 1, again, just in this sort of tuple, and we get a new state. So now we have SARSA, right? Then we pick the next action. That's the A prime. And now we update this Q function. We just literally plug it into the TD learning algorithm. And then you rinse and repeat. And if you just do this over enough time and with enough data, we actually will get to, and I should maybe add some MDPs will suck, right? Like some, if you have one MDP with zero reward everywhere except for one state, you're going to have to bounce around for an unbound amount of time, or a bound, but a very long time before you hit that particular state that gives you a reward. So you do have to think about that, but that's again a little bit outside of the context here. But if you just do this forever, you'll eventually get to a reasonable estimation of your state action function, which is pretty cool. So the next version of this is almost exactly the same. It takes a couple of times to take a look to figure out what's going on here and how is it different. But so Q learning is essentially SARSA, but it's off policy. And the reason it's off policy is we're actually not using the current policy to select the next action. We're going to be selecting the action that has the maximum Q value regardless of what our policy tells us to do. And I think that's a very, very subtle difference than SARSA, right? Because here we actually have an action. The action is determined by our Q value estimate, but we take the argmax and what have you, but we're updating our value function based on our Q value function that we're estimating. Whereas here, we're actually going to update the Q value based on what would give us the maximum action, regardless of what our action was. So it's a very subtle difference, but we're actually not using our policy to update our Q value function. We're using a potentially different policy that we may have used in the past to determine what that is. Now, in practice, it may just be the same policy, but that's why it's called off policy, because our updates are being extracted from the maximum Q value, regardless of the action we would have taken given our current Q value function. Which is weird because it's still based on our estimate, but it's based on an estimate of a state we haven't seen yet, so it's kind of like, it's a little bit, again, like lots of nuance here. So again, yeah, notice this gamma max, A of Q here in the TD target, versus in SARSA we don't have that, right? It's just going to be the discounted Q function of the action we would take per argmax of that. And it's kind of like, what? It's weird, right? Because that AT we're going to take is coming from our Q function. But in this case, we sample our next state given the state that we'd be in, right? So we are using our policy. Our policy, in this case, our policy defined by the Q state action function. And here we're not. Here we actually don't wait. We don't sample the next action. We just sample the Q value function directly for what that action would be. It's a very subtle difference because you can kind of see our action here would be the action that takes the maximum, but here we're just adding that as a value. We don't actually take that action at all. So it sort of like saves you time. And as a result, Q learning I think is seen as a little bit better, more state-of-the-art than SARSA, and you don't see SARSA as often, especially in deep learning, deep reinforcement learning. One of the first things we'll talk about, and I think this will be next week, or the next set of lectures, is DQN, or deep Q learning. Well, there's double Q learning, and then there's deep double Q, whatever. But when people talk about that Atari, like our reinforcement learning beating Atari games, that first science paper was a Q learning algorithm that what the kind of fundamental thing that was done there was, instead of using a tabular Q function, right? We've been talking about kind of like we have MDPs and we have these states that we know. Well, what do you do for like a video game where the states, they're like billions of states, right? Or in a continuous set of states. Like I don't even know what the states are. We can start to approximate these Q value functions, or these value functions, as deep neural networks. And if you can do that, then you can do all the same stuff as we've been talking about. And but instead of dealing with them in the tabular form, you're simply dealing with them in context of these deep neural networks. And if you can do that, then this just looks like supervised learning, as we've talked about many times, and you can do a lot of stuff. And so the first real, I think, result that got a lot of people to pay attention to these, function approximation for Q learning was actually using Q learning versus SARSA. So we'll talk about that more in a future set of lectures, but hopefully now you'll have the basis to talk about that. Cool. So next, we'll talk a little bit more about deep reinforcement learning, because we just touched on it a little bit, and also policy gradient methods, because that's a slightly different thing. Cool. See you there.